CMOS or CMOS logic. This is the logic you see in integrated circuits in microchips, microcontrollers. The C stands for complementary MOSFET. CMOS is a way to create logic in a microchip, that's where you'll usually see it, in a way that takes more transistors but is even more power saving than any other method. The idea is for computing devices so that they don't generate a ton of heat, because the more power you use, the more heat is generated by resistors and all this other stuff. And it also preserves battery life. We would not have handheld devices without CMOS technology, without MOSFET technology. We'd have to have backpacks with giant batteries in them to run our phones. Now you can do CMOS with discrete transistors, with discrete MOSFETs you can hold in your hand, but there's not really much reason to, because it doubles the cost of transistors. Every single place you'd use a transistor in a normal logic gate, now you need 2 MOSFETs. So it increases the cost extraordinarily. MOSFETs aren't that expensive, but you try to get a bag of 1,000, it might still be a few $100s. And also they'll take up so much more space that you're not going to make a 10,000 transistor device in a breadboard, which means the actual power consumption is going to be so minuscule it's not going to be a big deal. CMOS is seen in chips because in chips you don't have little transistors and little itty-bitty wires you connect them with. It's layers, and you etch, and you put a layer down and you etch, and it's constructed out of the materials directly rather than separate transistors. So that's why it works. You can pack them in, 14 nanometers or smaller in modern high-end CPUs. But what is CMOS? To make an inverter with an NPN, you have power, you have a resistor, your output, your NPN, and your negative. So this is your high, this is your low. If you give it high here, then the NPN is open, which means you've got a short to ground here, so you have a low output. If you have a low here, the NPN is closed, which means this is not conducting and you have a connection to high out. Simple inverter. You can do this with an N-type MOSFET exactly the same way. Give it a low, the gate will discharge to close and the whole thing will close. There won't be any conduction and you'll get your high. Put your high here and it'll be a short to ground through it and you get your low output just like before. That's actually drawn ill. There we go. So you can just swap in a MOSFET, it'll work fine. But the issue here is when this is high, when the MOSFET is open, you're getting your low output, but there is a continual drain. Remember how the BJTs draw current when they're on? Same thing here, it's going to draw current when it's on, not through the gate. The gate will charge to high and stop, and the gate current will stop minus a few electrons sneaking through. But there is a continual drain through this resistor, through the MOSFET to ground, in addition to whatever is going on over here, this nonstop drain. That's the problem. That's the power drain that we want to eliminate. Even though this will function, it's going to be too costly on our batteries. So what if we do something else? Let's throw away the resistor. Fun fact, you can actually operate MOSFETs with no resistors whatsoever other than on the load. I'll get into that in a future video, and generally you do use resistors, by the way. In case somebody's about to call me out, I know that there are resistors on the gates in many circumstances, but you technically don't need them, especially in a breadboard situation. We'll worry about that in the future. For now, let's have no resistors. What if I have my positive, I have a P-type MOSFET, my output, an N-type MOSFET, and my negative. So positive is our high, negative is our low. This is an inverter in CMOS. CMOS basically doubles your transistor cost. You need 2 MOSFETs everywhere you would use 1 MOSFET or BJT in a normal inverter, NAND, and XOR, whatever, gate. So this is one of many reasons why you just wouldn't bother to do this in a discrete situation, in addition to the savings not really being worth it. So let's say our input is high. So let's do high here and high here. It's an inverter, it's one input going into both of these. Well, we've got high on the source and high on the gate, so the gate capacitor, quote unquote, the gate capacitance, will discharge because there's no voltage across that. And this MOSFET will turn off, which means drain is a floating output. There's no conductance. But here, we've got high. I drew the L in the wrong place. You got the point. So we've got high on the gate here, low on the source, so this gate will charge up. The N-type will open, and there will be a connection to negative out here. The drain here is closed, no connection, but there will be a connection to low there. So we get a low, which is inverted. So the output of this pair is not floating. The drain is floating out of this gate, but that doesn't mean anything. So that's our low. Now let's say the input is low. Well, low and low across gate to source here, this drain is closed. Nothing's going through there. But high to low, source to gate here, this drain is open, connected to positive, and we get that positive out here. Drain is closed here, but this drain is open. So again, there's no floating on the actual output going to the next stage of logic. The individual gate has a floating drain, but whether the input is low or high, there is a positive, or affirmative, I should say, affirmative connection to high or low, no matter which one. So we can safely connect this to more MOSFETs because there's always going to be a connection, an affirmative connection to high or low. But also, in both cases, one of these is open and one of these is closed. The only current going out would be if there were a load here, and the current would be through one or the other of these, either out the P-type or in the N-type. So source to drain here or drain to source there. But nothing through. There's no constant drain in order to get this to happen. There's double the parts cost, more space, more wiring, but lower power. So when you are creating your chip and you're just etching the little pieces out, this is a great thing. That's the beauty of CMOS. There's no constant drain. The gates take current when they charge and discharge. I suppose only when they charge to a higher voltage, really, because when they discharge, they're just dumping what was already in there. So they use current when they charge to a higher voltage, and they use current if there's a load out, so the next gates would use current when they charge and such. Or if there's, finally something being driven, it'll be the normal load current. But nothing idle. When they're not switching, when there's no load, there's nothing. And so they're super power efficient. And there's your inverter. Well, what about a NAND gate? This is where it gets tricky. So we know it's double. So a NAND gate is 2 NPN transistors in series or 2 PNP transistors in parallel plus a resistor. Here, we're going to need, because we know we need double, we're going to need 4 MOSFETs, 2 Ps and 2 Ns. And they will be arranged like so. The P types will be in parallel. The N types will be in series. Now, regarding the notation, you'll see some places when they denote these transistors in series, you'll have like your 3 lines on this one and 3 lines on this one. Let me draw this a little higher. So what you'll have, remember, this is the drain, the substrate, and the source, and the substrate and source are tied together in discrete ones. Well, when you're doing a chip, they're not tied together. So you'll actually take the source of one into the drain of the other. Then you've got the drain of the first one is getting its input. And then you've got the source of the last one connected to your negative. And the substrates are all grounded as well out to this negative. This is the way you'll actually see it drawn. The way we have it hooked up with discretes is more like this. So we've got our 3, and we've got our input, and then we've got our output, but our substrates are tied together. So it's like this. So this is what we actually have, without worrying about the body diode. So this is kind of how you'd have it in a chip. This is kind of how you'd have it just putting them in a breadboard. And I've tested this. This works fine. You connect them like this. And even though the sources are connected and it's not like this, the sources and the substrates are all connected, this diagram is not the same as this diagram. These are different wirings, but it works. I did it in a breadboard. I made a NAND gate with 2 Ps and 2 Ns. Worked fine. So just try to not get confused by this. Just look at this. Don't look at all the little wires. Try to just say, okay, they're in series, and hook them up the same way you'd hook up BJTs. You have 3 pins. You have a drain pin, a gate pin, a source pin. So in series, you take a source pin, connect it to the next drain pin. That's it. Don't worry about the wiring too much. It'll work just fine. Although once again, you're probably not going to be doing this with discrete ones, but I just wanted to show you. That's why you see the wiring, and that's why it's weird, because they're drawing it with not shorted substrates, but it'll work just fine. So what happens here? This is our output. There's your output. So this is a NAND gate. Recall the NAND. The NAND is going to output high unless all of its inputs are high, because AND 2 highs is a high, so NAND 2 highs is a low. So if we do high, high on all of these, what happens? Recall that the positive is high, the negative is low. So a high on the gate of a P-type will turn it off. So neither of these are conducting, so the positive is disconnected. But a high turns on an N-type, so both of these are open. So we've got negative, This is open going out, whereas both of these are closed. So we have our low here. Now, if we change either of these to low, now recall, this is 2 input. I'll do this in 2 different colors if you can see them to help this. So on the left here, I'm going to say high, and on the top is high. So left P, top N is input 1. Right P, be low, bottom N will be low, so right P, bottom N will be low. That'll be input 2. So what happens now? This is high, P-type high is still closed, but this P is getting a low, so it's open. So the positive is connected through to the output. And what happens here? This N is on, but this N is off because this one's getting a low. So they're in series. They have to both be open for the negative to connect through. So this is closed off. This is N. Technically, this current can get all the way through to this source in between the two, but it can't get through this one, so it's still nothing happening. There's no base to emitter, anything going on if you hook them up in reverse. No resistors, no, none of that. It's still effectively closed off from negative, so you're only getting your high through the P. And you can see, obviously, if we switch it, we'll have the same thing. And if they're all low, if input 1 is also low, then both of these are closed and both of these are open, so positive is coming through both of those. So once again, we have the situation where there is no throughput, there's no wasted current through positive to negative other than what's going out the load, because there's never a case where both of these are open and either of these are open. The only time both of these are open is when both of these are closed. So there's no wasting, and there's also no floating output. There's always an affirmative connection to positive or negative, no matter the inputs. So there's your NAND gate. What about a NOR? Well, the beautiful symmetry. Don't I love symmetry? Let's put it in reverse. Let's take our 2 P-type MOSFETs and put them in series, and then the N-types, these in parallel. So there's the output. Positive is high, negative is low. So let's say input 1 is the top P. Oh, and the logic. So a NOR gate. We're doing a NOR gate now. The OR operation is low only if both inputs are low. If either or both inputs are high, the output is high. So both inputs low equals low, nor both inputs low equals high. So if we do input 1 is low, so top P left N is input 1, and then bottom P and right N is input 2. Both of those are low. So what happens? Low will turn off both N's, low will turn on both P's. So the positive is getting through, the negative is not getting through, the output is high. So there's no waste because both of these are closed, and we have an affirmative connection to high. If we take either of these, let's take input 2, make it high. Input 2 is high. Well, now we've closed off this P. So even though this P is still open, this P is closed. So the whole thing's closed because they're in series. But this N is open. So no waste through them and affirmative connection. So now the output is low. And if we have both inputs be high, change input 1 to high. Now both of these are open, so we still have a connection to negative, but both of these are closed. So we still have no connection to positive. No passing through, but an affirmative connection to low. And there's your NOR gate. And other MOSFET, CMOS logic is created in the same way. And there's little techniques you can do on paper to decide what arrangement you need for a particular truth table, but we'll leave that to the people making CPUs. If I ever decide to make discrete MOSFET logic with CMOS style, I'll just create a computer program to figure it out for me. That's what computers are for, aren't they? But there you go. That's the joy of CMOS. That's why it's so power conserving. There's no wasted current. The only current is during the switching and from the load. So the entire, you have a whole big chip covered with MOSFET logic, with CMOS logic. So every time you pulse the clock and all of the things switch, you'll take a burst of current. And then if you have something connected to the output pins of your chip, that can be using current. But other than that, your chip will sit there and do almost nothing. There will be microamps or less of just trickle. And that makes your battery happy. So while the batteries dance in joy and wonder, I'll be seeing you.